On se demande parfois pourquoi les Marseillais sont un naturel toujours gai. Ce qui les rend ainsi, c'est le soleil bleu qui brille en un ciel toujours bleu. Quand on habite un pays aussi charmant, comment voulez-vous qu'il en soit autrement? Au soleil de Marseille, quelle merveille, tout vous sourit. Sa douceur nous enivre, nous fait vivre, nous attendons. Les mots d'esprit, les blagues nous enchantent, même quand nous parlons, notre accent chante. Au soleil de Marseille, quelle merveille, tout vous sourit. Nous exportons partout mille spécialités, nos fleurs et nos fruits. Mais pour les gens du Nord, quand on fait un colis, avec le regret, c'est devenu si l'on pouvait s'envoyer que de nos soleils au monde entier.
Bonjour everyone, we are now on our fourth day of live LiveMEEG, and we are getting deeper and deeper in the ocean of good practices. We want to thank you all for yesterday's attendance. We reached summits during the software and signal processing sessions, and we are now close to 1,000 live attendees, including a cat, ducks, and pandicorn, which actually makes live LiveMEEG the first trans-species online conference ever done. Speaking of innovations, and regarding yesterday's session on perspectives for the Cutting EEG Association, we are grateful for your suggestions. By the way, you can still keep up writing us about your ideas. This is really motivating for us and helps as much as your donations. Speaking of which, some of you ask us if we can provide a certificate of attendance and a payment receipt. We can, that can be useful when making a donation, right? So the response is yes, every attendee will receive a certificate. So what about today? To improve our skills and avoid random and industrial p-value phishing, we will start with a landmark of good research practices in MEEG, the statistics. To dive into this, we invited Big Fish. They will share with us their advices and recommendations. Then there will be a satellite event on Artemis, a new reporting framework for ERP research, coordinated by Vanya Lovic and Susie Stiles. And later today, we will have more than a DJ in a gather town. So stay tuned, don't forget to be there. We hope that you will learn, question, and enjoy today's talks. It is now time for me to pass on to Captain Guillaume and board into the statistics session. Let's go, guy. It's time for a serious matter. Guillaume?
Yes.
Guillaume? It's yours.
All right. Hi, folks. So we have a great session today with 3 speakers, and in the interest of time, let's just dive in. Yeah, what an introduction. Yeah, I was told I would need something to recover. Yeah, I'm gonna get a little shot of coffee whiskey here. All right, so our first speaker today is Maximilien Chaumont, and he's going to tell us about statistical power in MEG data, spatial constraints for a reliable study. And you can ask questions in the chat if you want to, but preferably use at the bottom of the screen, you have a ask a question option, and there you can specify if who you want to answer your question. So put the name of the speaker the question is addressed to. It could be to all the speakers, and also mention if you want to ask your question out loud, so we can put you live on a video in a question session so that you can ask your question directly, or otherwise I'll just read it on the screen. All right, Max.
Hi, everybody. Thank you very much. I want to start by thanking the organizers for inviting me at this event. I've been attending Cutting EG since the very first edition, so I'm glad I can finally speak to you today. All right, so my talk is about statistical power in MEG data, and I will look specifically at spatial constraints in source space for a reliable study. So I want to, does it, no, it's not moving? Yes, it is. Okay, I want to start this talk with a simple question that is often asked at the beginning of an experiment. How many trials and how many subjects do I need to include in my experiments? Indeed, increasing the size of the samples we collect increases the precision of our measures, but there is a limit to both the amount of time that participants will be able to focus on the task at hand and the number of subjects that we have time and money for. Beyond these limits, the numbers will depend on the size of the effect that we expect in a given experiment. Yeah, the estimates in the literature vary, but roughly the number of trials required varies between a few dozen and a couple hundreds. Here, I want to examine the constraints imposed by our brain anatomy and the geometry of the brain sources. Namely, I will look at 4 different variables. First, the distance to the sensors, that is how the distance of a source from the sensor array influences how well it can be detected. Its orientation. We all, or many of us know that sources that are oriented in MEG tangentially to the head surface are easy to detect, whereas radial sources are invisible. I will also talk about cross-subject variability and how this variability in position and in orientation may affect our ability to detect these. So these are our questions for this talk. To tackle these questions, I took a simulation approach using data from the Human Connectome project, which contains MEG data for 89 subjects. It includes a brain model and like a subject head model for every subject. And this allows us to create a model of the influence of any specific source on the sensors. We also use resting state data from this same pool of data as a source of plausible physiological noise. So using these data, we simulated fake experiments in which we injected a known signal into some resting state data. We then tried to detect this signal using a standard experimental design, and a paired t-test across subjects. We repeated this procedure a large number of times so as to evaluate the chances that we have to detect a given source with a set number of trials and subjects. Because we know that the effect exists, this estimate is, in fact, an estimate of the statistical power of our method. Now, before I describe this procedure in somewhat more detail, I want to say a few words about the brain models that we use. These were constructed using FreeSurfer, which can create a source mesh with exactly the same number of sources in each and every subject. And these sources are ordered in exactly the same way in each subject, so that any source taken by its index in the anatomical mesh is anatomically homologous across subjects. Therefore, and I forgot to move my slides. Therefore, if I take a source, say, in the frontal cortex, like this one, for example, I can retrieve an estimate of how much this region is variable across subjects. So here you see that the red arrows indicate the position for a given source in each and every subject. And the black arrow is the average of all these sources across subjects. Okay. All right. And here I illustrate this for a few different brain regions. So you see, for example, this orbitofrontal region here, so in the orbitofrontal cortex, is much further than this frontal source from the sensors. So we expect that perhaps it will be harder to detect. On the other side here, this fusiform cortical region has all its dipoles oriented in pretty much the same direction. So we expect that it will be easier to detect than a region here in the lateral occipital cortex with random orientations. Okay, so now more details on how we simulate our statistical power. We consider here a very simple design with two conditions. One with signal added to from a specific source here. Okay, so we add this model signal to a random noise, resting state noise, to get trials from a signal condition here and a no signal condition or noise condition here. Okay, we then move these trials. So no, we don't move them. We just create as many trials as we need for our experiment. So say we want to test n trials, we take n trials, yes. We then average these across trials to get a single average for a single subject. We do that for k subjects, and we subtract this from the noise condition, which we create with exactly the same procedure. And we test this against 0 by means of a paired t-test and a corrected for multiple comparison. We consider a test to be significant if the peak sensor of the topography of the injected effect is found in a significant cluster. Okay, we repeat this now 500 times and count how many significant effects we found. And our estimate of power is then the number of significant effects divided by 500. So for example, here, if I do this with 50 subjects, 50 trials and 25 subjects, I obtain a power of 50% for the specific source that we modeled. I take this 50% and report it here in this graph. And I can then run this for all combinations of trials and subjects to retrieve a power contour map that will indicate to us how sensitive we are to this source. So in this example, we would need, with 25 subjects, we would need at least 60 trials in order to reach a power of at least 80%. Now, we do this for the two, I illustrate this now for the two sources. So this source that is closer to the sensors, this source that is further away from the sensors. Okay, you see here the topographies, the average topography for each of these sources across subjects, and the power contour maps that show that indeed there is a much lower detectability at larger distances. So with 25 subjects, you would have to do at least, say, 80 trials or 90 perhaps, in that case, in order to detect a source that you will be able to detect with 30 subjects in 25 subjects here. Now, using this brain anatomy, it is quite hard to disentangle the various properties that I highlighted at the beginning, orientation, distance, and variability of the two. From one another. This is because in the brain, the relationships between the spatial properties of the sources is quite intricate. Here I plot, so for all the sources of the brain, the correspondence or the scatter plots of each of these variables. So say distance to sensor with respect to orientation are plotted against orientation with respect to skull. And you see that there are some quite complex patterns of relationships across the various measures, which is hard to model, and so we are not able really to model this easily. And two distinct sources in the brain will hardly be considered to differ in only one of the properties that we indicated. So this is why we moved then to a more systematic investigation and looked so varied the properties that we were talking about individually. So here I took a source in the parietal cortex and varied its distance to the sensors, diving deeper and deeper in the cortex. We see here it's actually above the cortex. It's just for illustration, right? So above the cortex, we have a very strong dipole, and as we go deeper, we see it little and little, less. And you see here that the power indeed decreases quite linearly with the distance. Same investigation for orientation. We take the orientation with respect to the scalp. Here we start with the radial orientation. So each and every subject, it's radial with respect to its own scalp orientation at that location, the closest point. And we see that for the radial orientation, it's really difficult to detect anything. As soon as we go away from this orientation, we recover a very high power at this for this specific source. In terms of position variability, okay, so again, here I have one with no position variability across subject, and I increase this variability up to, I think, 2 or 3 centimeters in radius. And you see that even with the highest level of variability here, we still keep detecting this quite well. So it seems that position variability does not have much of an effect. This is quite comprehensible if we consider that actually all of these dipoles here will have about the same pattern of activity on the scalp, on the sensors. Last, I investigated also how the variability in orientation. So here I take a dipole with no variability, 30 degrees on average of variability, 60, 90, 180 degrees, so completely variable. Here the dipoles cancel each other completely, so we are really not able to detect anything, and with compared to a very highly collinear, like no variability dipole. Okay, so now I want to take a slightly different perspective. Instead of testing one source with many different trial and subject numbers, I take the different approach. I fix 25 subjects, 50 trials, and explore all the sources. Okay, and this is what you see here. So what we observe here is a very strong variability in power across the whole brain. So it means that sources that are along the central sulcus, in the medial wall, in some of the temporal regions, are very easy to detect with, or almost 100% of the times detected with 50 trials, 25 subjects, whereas other regions in the frontal cortex, in the lateral parietal and occipital cortices, the temporal pole, are much harder to detect, if not impossible, with this number of subjects and trials. So there is a very strong heterogeneity in detectability, right? Now, a final point I want to make is that there are different ways of computing differences between conditions. Either you just subtract them, as we did here since the beginning, or you can take the difference between the squared conditions. And this, in fact, enhances the statistical power for the peripheral source, not peripheral, but the superficial sources, as you can see here. And this is a map of the difference between the two previous ones. Okay, and you see that all of the cortical sources here are in blue, meaning that they are easier to detect with the squared differences than with the simple differences. And the pattern is reversed for the more internal or like more distant sources towards the center of the brain. And this is even more striking if we compute the differences in the global field power between conditions. in that case, you see that we're completely, in that case, saturating the power estimates for most of the cortical surface, a pattern that you also retrieve here. Yes. Okay, so with this, I want to conclude. So I hope I've convinced you that it is important to consider the spatial constraints on the sources that we are hoping to reveal with an experiment. And so the maps that I've showed you are hopefully going to, can be useful to understand where the power is, like our statistical power is good and where not. In particular, you may expect to increase the number of subjects and trials that you need to acquire in an experiment when investigating deeper sources. What a surprise. Radially oriented sources are very difficult to detect, so you may even have to go even further in terms of subjects and trials. And also highly variable sources, in particular in terms of orientation, are also very hard to detect. And the final point was also that you may consider using different contrast methods. If you want to detect peripheral, superficial sources, you probably want to use a GFP or squared differences or difference of squares approach. And with this, I want to thank you for your attention. Nathalie Georges and Aina Pius, with whom I'm collaborating on this subject. We're doing this together. Voila, thank you for your attention, and see you. I welcome questions. And I am very alone here in front of you all. No.
All right, so maybe we'll take one question now, and because we need to catch up with the original schedule. Thank you very much, Max.
Thank you.
There's a lot of discussion in the chat already. There was one question from Vladimir Litvak on the question is, could looking at a single vertex overestimate anatomical variability, because it would strongly depend on local smoothness?
Definitely, yes. So this allows me to bring one point. It's a very this investigation is really much more for me a way to incite everyone to look carefully at these variables. And of course, it's not realistic to look at these very specific one source. It's not something that you see in the real brain. So really, my goal here with this presentation and this work is to invite everybody to actually reflect a little bit on these details. So, but of course, simulating these with a larger patch, less variable in orientation in particular, would probably be very much advisable.
Mm-hmm. And from your simulations, can you tell us where you think we should invest our money? Is it in trials or is it in participants?
So this is really something that we'll need to look at in the future, actually, because so far I haven't seen any difference in the way that trials versus subjects are going to improve in one aspect or not another. But this is something I really want to look into, seeing how the intra-individual versus inter-individual variability can be coped with different numbers of subjects. Mm-hmm. Yes.
Okay. Well, thank you, Max. And
okay,
we'll get back to you soon after the rest of the talks. So we're going to move on to our second speaker today. Aaron Caldwell is going to tell us about using the Superpower R package to simulate power. And you can keep asking questions for Max, because we'll probably have time at the end for a roundtable where all the speakers can answer your questions. Hi, Aaron.
Hello, how's it going?
You can start whenever you want.
All right. Let me just select the right screen here. Perfect. There we go. So hello, everybody. My name is Aaron Caldwell. I'm a postdoctoral research fellow at the United States Army Research Institute of Environmental Medicine. Essentially, that means my research is mainly focused on human performance in extreme environments. So heat, cold, altitude. So I'm not an EEG researcher by profession, but I think some of my kind of extracurricular work on power analysis and statistics kind of broadly applies to any kind of experimental research. And so today I'm going to be talking about the Superpower R package, which I helped write and maintain currently, and how it can be used to simulate power. So you can use it for essentially study planning purposes, both to know how many subjects to recruit, as well as how to set your alpha and beta error rates. So quick disclosure, I do work for the United States Department of Defense as a postdoctoral researcher. None of the things I'm saying today can be considered an endorsement of my employers. So now that that's out of the way, we can get to the fun part. So a quick refresher on what power actually is, just so we're all on the same page. In frequentist statistics, we're typically concerned with two types of error, type 1 and type 2. So for type 1, think false positive, saying there is an effect when there isn't one, and type 2, false negative, saying there is no effect when there actually is a true underlying effect. So we try to control these errors when we're planning a study, at least from kind of the Nyman-Pearson approach to statistics or inference, by setting an acceptable alpha and beta error rate. So typically that's done with that 0.05, 0.2, right? So 80% power, that's that 0.2 beta error rate, and 0.05, which is typically that significance cutoff. One thing to remember is statistical power, that 1 minus beta, so 80%, is a hypothetical probability of detecting an effect of a certain magnitude. So we're essentially saying, like, if all of these things were true, what's the likelihood of us actually detecting the effect if it was there? And specifically under all of the conditions we've pre-specified. And then no effect would then be the alpha level, right? So just remember, as I'll get to the next slide, p-values are uniformly distributed under the null hypothesis. I think, one thing to remember is why do we care about power in general? Well, as you just kind of saw in the previous presentation, we want studies to find effects if they do exist. So if we're interested in some very small effect, so let's say like a lot of epidemiological studies, you're interested in some very small effect of a public health intervention. So if you were to collect a small sample size, say, as little in those studies as like 60 to 100 people, you'd be unlikely to detect that effect that you're very interested in, and that may actually have a large impact. And one thing I want to remind everybody is there's no free lunch in statistics. So yes, today I'm talking from this, very classical Nyman-Pearson approach, with alpha levels and power, but there's no free lunch. If you use Bayesian approach, or some more of an estimation approach to inference, you don't get away from the fact that small sample sizes aren't, very informative, especially if you're interested in small or variable effects. So just take that with a grain of salt. Even other approaches have an alternative to power. So visualization of what power actually looks like. As I mentioned, at this top row here, that's a simulation under the null hypothesis. So remember, p-values are uniformly distributed. So all p-values are equally likely under the null hypothesis. Yeah. As you move up in power, there's a shift of that distribution to the left, right? So you're going to get more and more of those p-values under that threshold, wherever it may be set. So how do we traditionally do power analysis? Well, at least in my background, which is in physiology, the people that do actually do power analysis, which probably is only about 50 to 70% of my field that actually report one, do it in a program called G-Power. You essentially set up an effect size of interest, usually a standardized mean difference as Cohen's D. As a quick note, you should never base this value on a previously observed value. If you do a pilot study and you get an effect size of 0.8, your power analysis shouldn't be based on that value, because the pilot study may be an overestimate, and you may be interested in a smaller effect size. So you may be setting up your study to be underpowered from the very beginning. And part of that analysis, typically people are when they're doing the a priori option within G-Power, you set an alpha and a beta or a power rate, and then a sample size is given as an output. And you say, yep, I need 21 subjects. I think this is a fine approach. overall. But the problem is most of our studies, at least in my field, aren't simple two groups or simple pre-post analyses, right? So as we have more complex power more complex experimental designs, we need a more complex power analysis to appropriately, set up our studies or justify our sample sizes. And that's where G-Power kind of really falls apart. If you have a, 3 time point, 2 or 3 between subjects groups, across all 3 time points, the program's not very useful because, one, the standardized effect size doesn't make much sense. And 2, very many times the power analysis software just doesn't accommodate those designs. And like I mentioned, the effect size isn't very intuitive. Cohen's D makes sense because it's talking about, kind of an overlap of 2 distributions. Cohen's F, at least in my mind, doesn't make much sense. Cohen's F of 0.1. I don't know what that means in real life for my study designs or my effects. So my partial solution to this, and I'll get into why it's partial later, is to simulate your study designs. And so what I've created is the Superpower R package. So if you're, R savvy researcher, you can, just directly type it into the console and get your results. And I've also created some Shiny apps. So for those of you who aren't R savvy, can, still use at least some of the functionality of the package. All right, so how does this work? First, you just set up your design. So it may just be, if you have like a 2x2 design, all between subjects, that would be 2B asterisk 2B, right? And that's telling the program what your design is. You then set up the population parameters. So you enter the mean, standard deviation, or standard deviations if you, aren't assuming homogeneity of variance, and then covariance, which, to make it easier, we just put in as a correlation. You can have a common correlation again, or you can have different correlations for different within groups comparisons. One of the big assumptions of the simulations within our package is it always assumes a multivariate normal distribution. This has many assumptions, which makes covariates very difficult. So right now, the package doesn't allow for covariates, but I'm hoping within the next year to have a new function that allows to add at least one covariate. So essentially the way the power analysis works is we set all these population parameters, sample sizes, and then we simulate. So we essentially sample from that population possibly thousands of times. And then from those samples, you get power, which would be the number of results that are under the alpha level you set over the total number of simulations, right? It's just essentially saying how many of those p-values get under the threshold. So one thing to remember is, as you're starting out, the lower the number of the simulations, the less accurate that estimate of power will be. And also what's nice about this is it allows you to actually see the effect of multiple comparisons on power. You can actually incorporate that. So I'll give you a quick example of what this actually looks like I can just do this actually. What this actually looks like in the Shiny app. So you can just set up the design. So in this case, we have 2 between, 2 within. So that would be like something like we're comparing old and young participants from pre to post intervention of some kind. You can enter factor levels and names. So I think I could do that. And I think it has a default setting in there. Yeah, so we have age, speed. We don't want it to different sample sizes per cell. We're going to have, let's say, 35 subjects. We're not going to enter multi-standard deviations. We're just going to enter 1 because we're going to assume homogeneity of variance. We'll just enter standard deviation of 1. Let's up that correlation because we have a very reliable measure, let's say. And then let's do something like this. And they both start at the same baseline, let's say. Or actually, let's even do this. 2, then 2.75. We set up the design. And then it gives us a nice little output here. Now you'll see it didn't do it right the first time. That's a little bug that I need to work out. There we go. And then our means line up with the plot as well as the standard deviations. Then you can check below to make sure the correlation matrix and covariance matrix line up correctly. It even tells you what the model it will be using within R to analyze those results within each simulation. Once we have that, we can go and actually perform the power analysis. Now, one thing to remember is if you set the seed, that's so the results are exactly reproducible. We don't want a sufficiency correction. Estimated marginal mean, so that's actually just looking at the pairwise comparisons within the study using the model. And then let's just put this down to like 500 simulations to make it nice and quick. And as we run it, it's got a little counter, which shows you where it is in the simulations. It's a pretty fast simulation, or it's gotten a lot faster, but we're working on actually making it a little bit quicker to make this process easier. So it's counting up the results, calculating, calculating, calculating. And there it is. Right there. Yeah. So then what this would tell us is that we only have about 45% power with 35 subjects to detect that interaction effect, right? So we had, differences at baseline and then differences in those slopes from pre to post, or from, I think it was slow to fast for the example. Once you're done with that, you can just hit download PDF report. Oh boy. Should give us a little warning box. There it is. And then we have a nice little report that, actually gives you text and some explanation, shows you everything you put in, right? And this is something we've actually, we created so you can, it's time and date, or date stamped at least, something that you can actually submit to, say, like a grant application or to your IRB to show you've actually done the work. All right, back to the PowerPoint. All right, so the other option is to use an empirical distribution. This essentially means the parameter estimates will be the same as the sample. This is nice because then it just directly calculates the effect size, and then we back calculate power from that. It's much quicker because only one simulation is run. However, it comes at a cost, right? Complex designs can't have small sample sizes because of this. So it's equal to, I think, 2 plus the product of the factors. So if you have a 3 by 3 by 3 design, you can't have less than 27 per cell to do that exact, but there's ways to extrapolate out from there, and you can't correct for multiple comparisons. So I have the exact app here. And I'm not going to go through the whole thing again because the process is relatively the same. You'll see less options because we can't do as much with the exact simulation, but we essentially just set it up. Oh boy, do I need to do some debugging? Nope, there it is. Okay, it's just running a little, my server's running a little slow today. And then, right, it's automatic because it's just doing that one simulation. And then what's nice about this is you can actually even run a power curve. And what you'll notice here is when I hit this, it's running through a range of sample sizes for the design. And what it should say is that I have 5% power because I have no effect within the design. Wow, the server's running super slow today. Well, it's pretty cool because it'll even draw a little line of where power is achieved. So there's nice little plots that come with it as well. Hopefully that'll load eventually. Back to presentation. Oop. All right, so some key questions are things that have come up when I've been emailing people about, both my apps and the R package itself. People ask me, hey, how do I know what my mean standard deviations and correlations should be, right, when I'm setting up the design? I don't know what the standard deviation is going to look like. Well, remember, power is a hypothetical probability. So when we set all of these parameters, right, what is our likelihood of detecting that effect that we anticipate seeing or want to see at least? So what I would say to most people is be skeptical and select reasonable parameters. Think about what your most skeptical reviewer or critic is going to say about your design, right? So if you have very small standard deviations, are your critics going to say, hey, why would you expect that, low of variance? Or if you have a very high correlation, like, hey, think about, if they're going to criticize that as well. Like, are those reasonable correlations for this design? One thing I do like about this is at the presentation, the funding agencies, IRBs, are going to be much more straightforward rather than saying some, kind of what I think is an esoteric standardized effect size. You're actually presenting the design, saying this is what our design looks like. This is what our power looks like for this study. And the way you state it, your design is you say, given these parameters, saying with the mean, standard deviations, correlations, we expect to have adequate, X% power with a sample size of X per group and an alpha level of Z, right? This way you're presenting your entire design and saying, with this design, with these assumptions, this is what we're going to see. Oh yeah, probably it's running a little slow because everybody's there. I need to update that server too. There we go. And then another thing to remember is you can also set your alpha and beta levels. I just made a big update to the package that's now up on CRAN and have 2 new web apps up both on Daniel Lawkins' site and my own. One thing I want you all to consider is the alpha and beta levels aren't fixed. Just like your sample size, you can adjust these as well. The current standard implies type 1 errors are 4 times as costly, and that's not always the case. I know in my field, is in many cases, they're even. And so what you may even want to do is calculate a weighted combined error rate, and that can be based on the cost or on your prior probabilities of each hypothesis. So Daniel has a simpler website to do this than my own. And essentially what you can do is you can say, I want to minimize the overall error rate. I want to actually, let's say, balance the two. And I think the alternative hypothesis is actually 2 times as likely as the null hypothesis, right? I have some prior data that would indicate that. Well, let's say we have a study where we're limited to, this is another case. Sometimes we can only say, we only can get 20 subjects, let's say, and we are expecting, let's say, an effect size of 0.65, or that's our minimum effect size. Well, what it does here is it actually tells you what your alpha and beta levels should be, right? And in this case, it's ridiculously, high, right? And in this case, you may look at this and go, maybe I shouldn't just do this study because, even when I try to balance the error rates, the overall combined error rate's way too high, right? It's not going to be a very informative study. And so that it's just one thing. Another thing to consider when you're going through design is justifying what alpha level you actually set. All right. Perfect. So just in conclusion, simulation is a powerful tool for estimating power. It's not limited to power. You can use simulation to actually estimate, your accuracy in your parameter estimations, how thin that the width of the confidence interval will be. It's also a great way of seeing how violating assumptions affect your model. Like I said, you can vary the correlation or the standard deviation. So that's a violation of the homogeneity of variance. And if you have repeated measures, if you have varying correlations, that's going to violate compound symmetry and, therefore violate sphericity. So you can actually see through simulations how that type 1 error rate and your power level are affected by violating those assumptions. It's also a great way to set up your analysis pipeline. The Superpower R package actually gives you like the model information. So you can essentially say like, oh, this is exactly how I'm going to analyze the data. This is what my data set should look like when it's, going through that analysis pipeline. Again, Bayesian or accuracy-based alternatives are out there. I'm actively seeking to add those to the package. So if you're using something like BRMS and R, there's ways to do this as well. I think Solomon Kurz has a wonderful tutorial on how to do a Bayesian power analysis. And lastly, don't forget to justify your alpha and power. They're not fixed values. Please, please, please just don't do 0.05 and 0.2 just because that's what the field is used to. And that's it. Oh, and just lastly, thank you all for having me here today. I'd like to thank my colleagues at Thermo Mountain Medicine Division. Special thanks to my mentor, Nisha Charkoudian, and special thanks to the collaborators who helped build this package, Daniel Hawkins, Frederick Aust, Lisa DeBryan, and one of my former mentors at the University of Arkansas, Rana Turner. Thank you. I'll take questions now.
Thank you, Aaron. We have a few questions in the chat. We have a bit of time. Thank you very much. Yeah, there's a bit of virtual clapping. So one thing. So you good point. You're warning people. Don't use necessarily the default. I would suggest you might want to change the default away from 0.05, for instance.
Mm-hmm. Yeah.
Just to annoy people. Just pick something very unusual. I'm all in favor of that. You want to get people thinking. There's a question from Robert Oostenveld. How to deal with multiple comparisons in relation to power estimation, given that with EEG, obviously, you'll have multiple channels and of frequency bands and so on. So is that something you plan to take into account? And what's your view on...
Yeah, it's definitely something you can take into account. So if you use the Monte Carlo simulation, so that's the one that's going through thousands of iterations, you can actually incorporate the multiple comparisons aspect and essentially, put in a Bonferroni, Tukey, whatever type of comparison you want. In that case, considering it's within subject, it would have to be something more like Bonferroni or Holm or the false discovery rate correction. I'm not as aware with EEG data, but what you may even want to do is use something more like a multi-level model. If you have, different, essentially a hierarchical kind of design where you have, frequencies within subjects, within groups. So that may be another thing. My package doesn't accommodate that, but there are others like SimStudy where you can actually just write your own custom code for a power analysis. So there's multiple ways to handle that. So you can do the multiple comparisons adjustment that we have within our package, or you can go to something more like advanced, like a multi-level model.
Sounds good. All right, I'm just checking quickly. We might move to the next speaker, and then we'll almost catch up with the schedule, and then we can see you all back for the roundtable discussion. Okay, so thank you very much, and we'll now move to our third talk from Steve Luck. It's going to be talking about standardized measurement error, a universal measure of data quality for average event-related potentials. Hi, Steve.
Good morning. Let me just get my slides going. Okay, looks like this is working. Okay, well, hello, everybody. I'm coming to you live from California, where it's a ridiculously early time in the morning. And it's got me thinking that it's 2020. Why do we still have to deal with this whole time zone thing? I mean, why should we be bound by the rotation of the Earth relative to the sun? We got to get the physicists to solve this so that we can all be at the same time of day when we're at these international online conferences. Okay, so today I'm going to be talking to you about a new measure of data quality that my lab has developed that we call the standardized measurement error. And before I actually get into it, I need to say a couple of things about the title. First, this is a measure of data quality for average ERPs. It's not a single trial measure. And we'll talk about it a little bit from now, how there's really no way to have just a generic measure of data quality. And so this measure of data quality is for average ERPs. If you're doing single trial research, that's awesome. You'll have to come up with a different metric. The other point that I wanted to make is that it doesn't have to be event-related potentials. It could be event-related magnetic fields. You could adapt this easily for time frequency analyses. During Max's talk earlier today, I was thinking about how you could actually use this to quantify the precision of your estimates of your source localization estimates. So you'd be able to say not just here's the answer, but here's the variability in our answer. Okay, so I like to always frame this in terms of this sort of crazy, ridiculous idea that I think we have all accepted, which is that you can actually record meaningful brain activity with electrodes that are on the skin over your skull, quite far from the brain with that big resistor of the skull in between. And this is really a preposterous idea if you think about it. In fact, when Hans Berger first discovered it, nobody believed that it was possible. Of course, it is possible, but it's challenging. And we have a lot of noise in our EEG, our MEG, all of these signals. And so when you go into the lab, you might see data that look like this. So do you believe that this difference between condition A and condition B here is real? I don't believe that. And these data are from my own lab, but it's just so noisy looking that it makes it hard for me to believe that this difference is anything other than noise. But that's a subjective judgment that I'm making. Wouldn't it be nice to have an objective measure of data quality? So you could go beyond just saying, well, that looks noisy, and actually quantify the noise level in a meaningful way. If we could do that, that would allow us to determine objectively which subjects' data are so noisy that they should be excluded, as opposed to doing that subjectively, which can be highly problematic in terms of biasing your results. You could also determine which electrodes are so noisy that they should be interpolated. More broadly, you could determine which data collection procedures, which signal processing procedures actually yield the highest data quality. Right now, every lab kind of has their own pipeline. They do things in their own different ways because it's hard to know which ways are really the best. Well, if we had an objective measure of data quality, we could determine which procedures actually give us the best data quality, and then we could all adopt those procedures. Okay, finally, you could use this when you're reviewing an article or reading a journal article, whether the data are so noisy they shouldn't be believed. I think we've all had that experience where you look at the data and you go, this is so noisy, I don't really believe the results. But wouldn't you like to have an objective criterion for that instead of just saying it subjectively? So our goal in developing this new metric of data quality was for you to be able to do this sort of thing. And we call this metric the standardized measurement error, or SME. And we have a preprint available that describes everything. Hopefully we'll get this submitted within the next couple of days. I also want to point out that we have an OSF site that has sample data, scripts, that sort of thing, so you can play around with this yourself and see how it works. Okay, I want to start by not telling you how it works, but what we were trying to achieve. What are the properties we wanted in a metric of data quality for average ERPs? So the first property we wanted is to get a separate data quality value for each individual participant, and actually for each electrode site, each condition. So typical measures of reliability give you one metric for the entire study, so you don't know which participants are good or bad, which electrode sites are good or bad, etc. So we wanted something that was at the individual subject level. And that would allow you to do things, for example, like when you see a channel that does this sort of thing where it's wandering around, you'd be able to ask, okay, is that so noisy that we should interpolate that channel? So getting down to the level of individual channels, individual subjects is important. But we still want to be able to aggregate across participants so that we can come up with a single metric of the overall data quality of a given study. And the metric we came up with, it turns out, is directly related to statistical power. And that's a very nice thing. You'd be able to ask, to what extent is your statistical power being impacted by the noisiness of your data, the quality of your data? The second property we wanted is to have this metric quantify the extent to which the noise impacts the specific amplitude or latency score that you're going to be putting into your statistical analysis. So here's what I mean by a score. It's just like an amplitude or latency measure, but I'm using the term score because lots of things are measures. We have a measure of data quality for a given measure. It gets too complicated. So I'm going to talk about scores. So imagine you've got this sort of rather noisy waveform. You've got a P3 wave here and you want to score its amplitude. So one way you could score it would be with the peak amplitude. I'm not a big fan of using peak amplitude, but it is a very common way of scoring the amplitude of a component. Another possible score would be the mean amplitude during perhaps the time range of 300 to 500 milliseconds. Maybe that's not the optimal time range in this study. It's just an example that I'll be using throughout. So we have multiple different ways we could score something. And our goal with our metric of data quality is to determine the extent to which the noise actually impacts the score of interest. So if you notice here, we've got a lot of high frequency noise. That's going to really have a big impact on the precision of the peak amplitude. It's going to cause a lot of subject to subject or experiment to experiment variability in peak amplitude. But high frequency noise like this has very, very little impact on the mean voltage over a 200 millisecond time window. The uppies and downies kind of cancel each other out, and the high frequency noise doesn't matter very much at all. So the effect of noise depends on how you're scoring your data. So there's no such thing as a generic measure of data quality. The data quality depends on the nature of the noise, the nature of the signal, and how you're scoring your data. So our goal was to have a metric of data quality that reflects the effect of noise on the specific score that we're using as the dependent variable in our statistical analysis, because that's where the rubber hits the road. I don't care if it looks noisy, if it doesn't actually impact my effect sizes, statistical power, etc., doesn't matter. But noise that might not look very bad might actually have a big impact on your power. So we want a metric of the effect of noise on the score of interest. Okay, our third property is that we want this metric to quantify the precision of our amplitude or latency scores. So what do I mean by precision? Well, I mean what the physicists mean by precision. What the physicists mean by precision is it's the extent to which scores are similar if you try to measure the same thing multiple times without any change in the thing that you're trying to measure. So if you take the temperature of a beaker of water, Same beaker of water, take the temperature multiple times. The precision is the extent to which those different measurements are similar. So high precision means all the values are similar. Low precision means that one measurement doesn't give you very close to the same value as the others. Now, the assumption that you're making here is that the system that you are measuring isn't changing. And of course, that isn't true when we're measuring anything from a human being, at least an alive human being. So when we talk about precision, we're thinking about the idea that imagine you could measure somebody's ERPs many different times without changing the subject. So that's all that's varying is the random noise. And of course, that's a theoretical construct, but that's what statistics is, right? It's always a theoretical construct. Okay, so here's an example of how you might quantify precision. Imagine that you run a subject in a session and you quantify that subject's P3 amplitude as the mean voltage from 300 to 500 milliseconds, and you get 8.18 microvolts. Now you take that subject and you bring them back for a second session. You measure the same thing again, but this time you get 7.7 microvolts. Then you bring the subject in a third time, and this time you get 4.67 microvolts. Now we're making the unrealistic assumption that if we were doing this, the subject isn't learning, isn't becoming fatigued. All that's varying is the random EEG noise. That's the only thing that's varying from session to session. So it's a theoretical idea, but it's a useful way to think about things. Okay, so if we were to do that, bring each subject in multiple times, for a given subject, we could quantify the variability of the different measures we get in our different measurement attempts as just the standard deviation of these values. So each time we run a session, make an average ERP, and we measure the score from that, and then we take the standard deviation across the different scores. So this standard deviation across many different measurement attempts is actually just a way of describing the standard error of measurement of the score. So our metric of data quality is really nothing more than the standard error of measurement of the score that you're obtaining from your average ERP waveform. So that's what we are achieving in this piece of work. So when we do this, when we get an amplitude or latency score from an average ERP waveform, we call the standard error of that score the standardized measurement error. And the reason we gave it a new name is there are lots of different things that standard error can refer to. And what we're using it to refer to is a little different. So we're trying to give it a different name. Okay, now the way I've described this so far, you have to bring each subject in for multiple sessions to measure the variability across sessions. And that's unrealistic in practice. So what you'd really like to do is run one session and estimate what you would get as the standard deviation if you repeated the session multiple times and took the standard deviation of the scores that you got for each session. So we want to take the data from one session and estimate this thing that would happen in theory if we could bring the subject back multiple times without any learning, without any fatigue, etc. Okay, so imagine we do this, we have an average ERP, we're going to measure the mean voltage from 300 to 500 milliseconds in that average ERP. Turns out that it's justifiable to quantify the standard error of this mean voltage from 300 to 500 milliseconds by going to the single trials, measuring the mean voltage from 300 to 500 milliseconds on each single trial, and using the conventional formula for the standard error of the mean. We just take the voltage from 300 to 500 milliseconds, mean voltage on each trial, get the standard deviation of those values and divide by the square root of the number of trials. This is something I'm sure you've all calculated many times in different contexts. Okay, so we could do that, but I want to remind you what it is that means. So even though now we're measuring from the single trials and using this formula, what we're trying to estimate is what would happen if we repeated the recording session many times, made an average ERP from each session, measured our score, the mean voltage from 300 to 500 milliseconds, from the average ERP from each of those sessions, and then took the standard deviation of those measures that we got from those individual sessions. So this formula gives us a convenient way to take the single trial data to estimate what would happen if we repeated the experiment multiple times and measured from the average ERP each time. Okay, so a small standardized measurement error means that we're estimating that we could get very similar values each time, and a large SME means we would get very dissimilar values each time, according to our estimate. Okay, so now let me give you an example of some real data, and all of this is available on our OSF site. So this is data from just a very simple oddball experiment where subjects are seeing letters or digits presented at the center of the screen. We have 100 trials, 80 of them are letters, 20 of them are digits. So the digits are the oddballs and the letters are the standards. Actually, the experiment is fully counterbalanced, but we'll keep it simple and imagine you're doing digits versus letters. Digits are rare, letters are frequent. So we've got oddballs and we've got standards. Okay, here are the data from 4 of the subjects in this experiment. And the red line is the oddballs, the average ERP from the 20 oddball trials. The black line is the average ERP from the 80 standards. And you get a somewhat bigger P3 for the oddball than for the standards, but it varies a lot from subject to subject. Now, if you just eyeballed these data and thought, which subject has the noisiest data? Well, when I looked at this, I thought it's subject 3. I mean, look at all that noise in the pre-stimulus baseline. There's a lot of what looks like unaveraged out alpha. So this subject seems like the really noisy one. But really, is that noise that we're seeing here going to impact our ability to precisely measure the mean voltage from 300 to 500 milliseconds? Well, it's hard to know from looking at it. If you actually compute the standardized measurement error, you get one value for the standards, another for the oddballs in each individual subject. And the first thing I want to point you to is that the standardized measurement error is about twice as big for the oddballs as it is for the standards. Now we have 4 times as many trials for the standards as we have for the oddballs. And I'm sure you've all heard that the signal to noise ratio of an ERP goes up as a function of the square root of the number of trials. So if we have 4 times as many standards as oddballs, the signal to noise ratio should be twice as good for the standards as for the oddballs. So the fact that the standardized measurement error is twice as big for the oddballs as for the standards is exactly what you'd expect. Okay, and that's just a natural fact of the way we're computing the standardized measurement error, which is the standard deviation divided by the square root of the number of trials. So all else being equal, it should vary linearly with the square root of the number of trials. Okay, now I want you to focus on the fact that these 2 subjects have quite a bit higher values than subjects 2 and 3. So the top and the bottom subjects, their SME values are more than twice as big as the other 2 subjects. So what that means is the top and bottom subjects have the noisier data with respect to our ability to estimate the mean voltage from 300 to 500 milliseconds. So the subject 3 here, who looks really noisy, actually has relatively clean data. This noise doesn't seem to be impacting our ability to estimate the mean voltage from 300 to 500 milliseconds. Okay, when we look at the single trials, we see why this is. So I've just taken 10 single trial epochs from each of these subjects and overlaid them. And now you can see that these middle 2 subjects don't have a lot of trial by trial variability out here in the time period that we're measuring. Whereas this subject down here has tremendous trial by trial variability. This is somebody who probably has a lot of skin potentials and the voltage is just kind of wandering around, as you often see in some subjects. So when you're trying to measure the mean voltage out at this relatively late time period, these low frequency drifts really kill your ability to precisely measure. Whereas something like alpha, it's not such a big deal if you're measuring the mean voltage over a 200 millisecond period. Okay, so hopefully that gives you a little bit of a sense of how you can use this and get some information out of it that is not obvious just from looking at the data. Now you might be wondering, how can I do this myself? Well, it's not too hard to program this yourself, but if you use ERPLab Toolbox, it is now built in. And the standardized measurement error is actually automatically calculated whenever you make an average ERP waveform for a given subject. And it does it using a set of default parameters. Basically, it gives you one value for every electrode site in every condition in a set of 100 millisecond wide time intervals. So you can see what your data quality is during each one of those periods for the mean voltage during that period. And if you want to use some other period for your main analysis, you can easily specify any custom time window you want and get the standardized measurement error for the mean amplitude over that time window. So very straightforward. And we have in our GitHub site, we have a whole page that describes the big picture. We actually provide some other metrics of data quality as well. Okay, what if you're not measuring the mean voltage over a fixed time window? What if you're trying to measure something else, like a peak amplitude or some latency variable? Well, this formula of taking the single trial values, taking the standard deviation of those, and dividing by the square root of the number of trials can be used only when you're using the mean voltage within a time window as your score. It is not a valid approach for other kinds of scores. So if you're trying to measure peak amplitude, although I hope you're not, because it's really, in most cases, a terrible measure, but sometimes people do, or more likely, you're measuring something like a peak latency or an onset latency or the 50% area latency, any latency measure, this equation is not going to work properly. And I'm going to leave it for the paper. You can read our preprint to see why that is the case. But the key thing is that for these other measures, you can easily estimate the SME using bootstrapping. It's a little computationally intensive, might have to run overnight in some cases, but it will work for you. Okay, and if you want to see examples with bootstrapping, which requires a little bit of scripting, we have examples on our OSF site. So you can see exactly how to use bootstrapping to compute the standardized measurement error for something like a peak amplitude or peak latency score. Also, using bootstrapping, you can get the standardized measurement error for something that's derived from some recombination of your data. So for example, imagine you're looking at the lateralized readiness potential and you want to measure the onset latency from a contralateral minus ipsilateral difference wave. Using bootstrapping, you can estimate the standardized measurement error for that measure, even though it's obtained from a difference wave. So this is very, very flexible. And we call it a universal measure of data quality for average ERPs because it can be used for just about any score. I have yet to see a case where it wouldn't work as long as it's a score derived from an average ERP. Okay, I'm going to briefly say a few words about how this is related to statistical power, but really just a few words. You'll have to read the paper for the details. But imagine we do a very simple study. We've got two groups of subjects. We're measuring P3 amplitude in those two groups of subjects. We get means, we get standard deviations, and so we can estimate our effect size here. And, you know, it's the difference in means divided by the pooled standard deviation. We get an effect size. And from that effect size and the number of subjects, we can estimate our statistical power. Now, when you do this in an actual ERP experiment, you look at these error bars. Now, these error bars are the standard error of the group mean, which is very different from the standardized measurement error, which tells you about the noise level of the single subject data. What you really want to know with respect to noise here is how much of the variability across subjects that you're seeing is due to measurement error, is due to the trial-by-trial variability in the EEG or MEG signal. How much of that is measurement error versus how much of this is true differences between subjects, real differences that you can't get rid of? So that's an important question because by answering that question, you can answer further questions like, well, what would happen to our effect size if we were able to reduce the noise in the EEG by 50%? Or how much would our power decrease if we reduce the number of trials by a certain number? So these manipulations of EEG noise or number of trials impact the data quality, they impact the standardized measurement error, and you can actually use the standardized measurement error to estimate how much of this is due to noise in the data and how your changes in noise level or number of trials would impact your effect sizes and therefore your statistical power. So to do this, you just need to aggregate across subjects. You measure the standardized measurement error in each subject, and then you just take the RMS of those values. You just square each subject's value, divide by the number of subjects, then take the square root. If you aggregate across subjects that way, it's very simple using basic math, because that's all I know how to do, to figure out how this is going to impact your effect size and statistical power. Okay, I'm going to finish up here by talking about how you can use the SME in your own research. So within your own lab, you could use the SME to determine which subjects should be excluded, which channels should be interpolated, and do that in an objective way, in an unbiased way. You could also use it to test whether some new recording procedure or analysis procedure actually improves your data quality. Not just eyeball it, but actually have an objective metric. Now, the real value of SME, I think, would be if everybody started reporting it, or if everybody started reporting some measure of data quality. If everybody reported their data quality in their journal articles, we could objectively determine whether the data from a given study are unacceptably noisy. So the data from that study should not be treated very seriously. More importantly, we could determine which recording methods, which experimental paradigms, which analysis procedures yield the highest data quality. And if we could do that, because everybody's now indicated what their data quality is, we could see which procedures give us the data quality, then we could all adopt those procedures, and this would increase the statistical power and replicability for everyone. So I really want to encourage you all to use this metric or come up with your own. But if we really need a standardized metric that everybody reports so that we can have these benefits and the field will progress much more rapidly. It's kind of scandalous that we don't already have such a metric. So we really need to start moving toward publishing measures of data quality along with our regular descriptive and inferential statistics. Okay, that is it for my presentation.
Thank you, Steve. Well, I have a few minutes left for general questions. I have one question to get started for you about this measure. So I get the intent; it's quite useful, but the problem is that it depends on sample size. So how would you be able to compare across experiments or participants if you don't have the same number of trials?
Well, the goal here is to ask what is the fundamental data quality, which is a function of the number of trials and the trial by trial variation. Now, you could, it would actually be pretty straightforward to factor out the number of trials as well and ask, basically you just don't divide by the square root of the number of trials, and that will give you the standard deviation across trials, and that would be independent of the number of trials. So you could report that, but I think it's in most cases, what you really want to know is what's the precision of the score I'm putting into my statistical analysis, which very much depends on the number of trials. And some procedures allow you to collect more trials than others, shorter intertrial intervals, etc. So it really is a part of the mix.
Sounds good. The only comment I have, the other comment I have is the checking the questions too. Is essentially what you're computing is a bootstrap estimate of the standard error, which is an inference about the population. Well, you're looking at the variability across a fictitious number of experiments across the population. So you're going to have some issues with some statisticians because essentially you're looking at something at one level to say something about your sample. I know it's a tool, but the interpretation of the standard error is very clear in statistics. There's just no alternative definitions to that. So I guess that's maybe one reason you're trying to give it another name. I'm just wondering whether it's a good idea to muddy a bit the definitions?
Well, that's for the field to decide. Other people can call it standardized measurement error if they want, and they could just call it the standard error if they want. I want to react to one of the things that you said leading up to that, which is that you have the standard error requires you to think about a sample from a population. And we're talking about the standardized measurement error from a given subject. It's a population of trials. And when you run an experiment, you can think of that as you're sampling from an infinite population of trials. And then you're asking, okay, what is the precision or the standard error of the measurement that I get from that? And so from the point of view of a single subject, it really is just the standard error of measurement. And that's straightforward. When you want to combine across subjects to ask about the statistical power or the effect size, then it's complicated only for the reasons it's always complicated to combine across individuals and trials at the same time. So I don't think there's anything about this metric that is any more complicated than anything else we do with respect to that issue.
Mm-hmm. No, it'd be good to get people thinking about what they can do with the Bootstrap, because it's a fantastic tool that's really can be applied to anything, which you've described very well. All right, can we bring the other speakers back for a few minutes of group discussion? We have a few questions in the forum. We had one question which was addressed to all. So Steve, you could start answering that from Amy Fairs. How do we design our studies well in terms of numbers of participants and trials when we know that the literature is biased towards significant effects? A pilot study may overestimate or underestimate the size of an effect, and calculating effects from the literature is also biased. And simulations are a challenge because we don't know exactly what to expect in our signal. Yeah, looks like doomsday crystal ball reading, but I'll let you answer.
So my answer for this is the answer that I got from my graduate mentor, Steve Hilliard, which is that in the end, replication is the best statistic. So I never trust the results of any single experiment. And so my view is that power analyses are an imperfect tool, and you can't expect them to do more than what they're intended to do, which is to give you a good guess about what's realistic and to decide, like, is it even worth doing this study or not, given the number of subjects I can afford to do? So I don't think we should ever expect a power analysis to tell us the true power that we're going to get in our study. It's an approximate tool. It's a great, useful tool as long as people treat it as an approximation.
Yeah.
Totally agree.
Sounds good to me.
Not
you shouldn't, basically, we should, the problem you get, all the time is, how do you deal with, I'm a new researcher and I need to do, a few experiments to make a name out there, knowing that you can't say much from one experiment. One experiment is just one experiment. When we run simulation, we do simulations of 1,000 or 10,000 simulated experiments, and we can tell you, well, in the long run, that's what you can expect. But people have just that one tiny experiment, and they need to publish it. And there is the pressure to make a big deal out of that one experiment.
I'm a big believer in multi-experiment papers where experiments 2, 3, and 4 include a replication and extension of experiment 1. It's shocking to me how few ERP papers have more than one experiment.
Yeah, I would add to that, this is where confidence intervals can be helpful in talking about a range of plausible effects. There's a wonderful R package called Concurve, which actually will plot the effect and the confidence intervals as a curve of plausible effects, with like the peak being, the point estimate. So I think talking about, if you have that one experiment, talking about a range of plausible effects and likelihoods of different effects is a helpful way of interpreting the data when you only have that one snapshot.
But when you're that young researcher trying to make a name for yourself, reviewers are not going to go, oh, well, there's some uncertainty here. They're going to say, okay, send this to some lower tier journal. So it's a very difficult sociological problem.
Yeah, we could probably solve by changing the standards. If all the journals were just expecting to have more evidence before being able to claim that there is an effect, then all those problems would go away. I just feel very sorry for someone who's young in the profession and trying to make a name. It's trying to, saying that that's the way we should do it, and the concrete reality and all the pressures that needs to be balanced. All right. We had a question from Max. Do you think, from Gal Vishnu, do you think these figures will be similar for EEG? And if not, are you also computing this for EEG?
Second answer, no. First answer, yes, definitely. Except that there are some properties of the magnetic field are different than those of the electric field. So, for example, the orientation with respect to the scalp is not going to impact so much the EEG power. But apart from that, the general principles are really the same. And I think that's all I can say. It's very much similar, but pay attention to the fact that the two modalities have very different properties. Yeah.
All right, a question from Raza Gulbinite to all speakers. In the first talk, what was the length of the trials that were simulated? I'm always puzzled by the emphasis on the number of trials in power analysis rather than the length of the signal.
You saw me. I mean, you caught me. 50 time samples we used. So it's I mean, it's a very first try, you know, like we're taking these tiny little almost time points, actually changing from a few, like from one time point to 50 time points doesn't make much of a difference in that case, in our case. But generally, yes, we used the very tiny time window and put the emphasis on the spatial resolution and on the number of trials and subjects. But of course, increasing the duration of your trial is going to make a difference. Yes, although I mean, you have to take into account the frequency profile of your trials. If you have some very slow waves, you are not going to be able to. You are not going to have such a strong effect if you increase the duration as opposed to if you don't. I don't know if I made myself clear, but
Okay.
yeah.
Maybe it'd be related to that sort of expansion of, you know, power analysis. What sources of variability do we need to take into account? There was a question to Aaron, but I think it applies to all of you. In EEG studies, we often see inter-individual variability due to skull thickness, for instance. So we should incorporate this uncertainty in our statistical models and relative power analysis. So Aaron, do you have plans to expand superpower with power analysis for multi-level models? Because that's something that hasn't been discussed here. That's discussed more and more, which is to integrate sources of variability in a model that can account for more factors than we typically use in EEG and MEG analysis.
Yeah, absolutely. You know, that process, Lisa DeBryan, that's actually who I've been working with a lot on this. We're really at the discussion stage because I think the big issue for me is getting something built into a single function is very difficult because, you know, that's why superpower is very unique is you can do any, you know, 3-factor ANOVA type design. And it essentially, you know, works. You know, there's not multiple functions for, you know, within certain levels of within and between. So getting something that works for a hierarchical linear model that would allow researchers to have, you know, a multitude of options and make it very flexible is very difficult. So we're working on it. We'll see what we can incorporate. I don't think we'll ever get to the point of I want to incorporate a Bayesian approach like with BRMS, but I think there's even so many more levels of complexity there that it'd be hard to incorporate into one function. The thing I can say to you though is you can write custom code to do this. So I use a lot of multi-level models for the studies I'm currently planning here at USAREM. And for those, I write custom code from the SIM study package. So that's actually where I'm generating the data from. And so you can actually generate, you know, multi-level clustered data from that. And it doesn't even have to be, you know, that multivariate normal Gaussian based data. You know, you can do binomial, negative binomial, Poisson type responses. So my suggestion is at that point, you kind of have to learn how to code and write a custom kind of for loop or replicate.
Indeed. And there was a question related, addressed to Steve that's directly related to that, which is essentially instead of trying to measure single trial viability, so within participant viability, why not just use hierarchical model in which you can directly model that that viability explicitly?
Oh, that's a really good point. So if your score is a mean voltage during some time window, why not just measure from the single trials? Why are we measuring from our average ERPs to begin with? And the answer is really just history, right? Where things developed from. But certainly my lab is moving in the direction of going to the multi-level models for that sort of thing. And so, you know, the tool that we have, the metric that we have is for like the way most people do their research now. But hopefully it will become totally obsolete because everybody will move to these multi-level models.
I think we're going to end on that. So we're all moving to multi-level modeling, and that's the future.
Yes.
Thank you all. I
Right.
think we covered most of the question in the chat and in the ask the question box. There was well, thank you very much for a great session, and we have more time if we want to. Okay. Well, I was trying to be a good chair and be on time. Okay. So we have more questions then. Okay. So Natalie George is saying, aha, linear mixed effect modeling for trial level inferences. Yes. In some fields they do that routinely. If you do psychology of language, most of the research now is done with psycholinguistics, is done with hierarchical model that takes into account item variability. We should definitely do that in most fields. The idea that, for instance, the assumption that for each stimulus, essentially the brain response is the same, which is what we do when we average across trial, it makes absolutely no sense. It's like saying, like, you present any face or any word, you'll have the same brain response. It is completely ridiculous. With hierarchical models, you can take that into account.
A question for you guys. The LME package is still the way to go to do multi-level hierarchical modeling in R in particular, I think. Is it? Aaron, perhaps you're...
Yeah, I mean, it's... so I actually originally was taught like a lot of statistics in SAS, and I have to say what SAS can do versus what LME4 can do is there's a wide gulf between them. Now, LME4 I know is still being developed and it can get there, but like just proc mixed within SAS is far more powerful. And as chat is saying right now, I would say, you know, if you're going to use R, BRMS is probably a better way to do multi-level modeling. The only reason I use LME4 is because I like using R. I don't need some of the things that the advanced modeling can do. And anytime I say Bayesian, all of my colleagues' like eyes get wide and they're a little scared. So yeah, LME4 is fine. It's just limited.
With BRMS, though, I think I understood that you need to specify really your priors, and like the design is a bit more complex, isn't it?
Yeah, it's
like
far more complicated.
The default values is not the way to go and do this properly, right?
I mean, you can, like, I'm just getting into that as well. So, you know, I've not actually implemented it other than just, you know, playing around with it. But yeah, I mean, it's more difficult. It's going to be more time consuming to do the modeling, but like you're going to have a lot more flexibility, which I guess can be a good and bad thing.
A word on what is BRMS, perhaps, for those who don't know.
Yeah, I'll put the link. I'll put the link. But what you have to consider too is the alternative. When you do a standard frequentist test, you have a prior probability. Your prior is always flat, and you expect that any value is plausible, which also makes no sense whatsoever. So you know, you got to put things in context. The huge advantage too of a hierarchical model is that it brings robust estimation because you have natural shrinkage. So that if you have noisy estimates, like noisy participants, their values will be pulled towards the average. So therefore, you have built-in outlier control. So do we have more? There's something from Inapius. We should also be looking at the profile of activity at the time that the stimulus itself is presented, as it will have effects on task-related behavior. All right, there's the question for Max. What about the difference in MEG systems? It looks like these results are related to gradiometers. Can we assume that the combination with magnetometers might access more complete projections of these sources?
Yeah, the HCP dataset is done with 4D BTI system that has only magnetometers. So the data, I believe, is from magnetometers only, the one I'm using. any system has its own level of noise. Any recording session has its own, like from day 1 to day 2, some channels are bad, some others are better. So it's never possible to really consider that a specific, or it's not possible to consider that the system that was used by HCP to do this data analysis is in a way like really directly transposable to another MEG system. So definitely one would need to run this with on different systems. Yeah. Though Robert says, I don't expect it to be different from the 2075 channels CTF or the 306 channels of NeuroMag, even though the 306 NeuroMag are like a third of them are, or 2/3 of them are gradiometers, I guess.
Okay, question for Steve. Before you estimate the ERPs or your data quality measure, do you high pass or low pass filter EEG signals? And can this affect the results?
Filtering very much impacts the results, right? So, and what you could do with our measure, here I'm going to advertise the measure, right? Is you could ask, what filters do the best job of improving the quality of the data for the score that you care about? So for example, I've said for years, you don't need to low pass filter your data if you're measuring the mean amplitude over any reasonably large time window. It really doesn't help much, except that it reduces your temporal resolution, because that's what filters do. So you would want to obtain the SME for the data filtered as you're going to filter it for scoring your data and putting it into the statistical analysis. And then of course you can play around with different filters to see what works best, but probably best to do that as information for the next study you do, rather than, try a million things and see what works best in the current study.
Yeah, definitely don't do that. Although it seems to be common practice given the number of studies with a gazillion statistical tests and the introduction that magically pinpoint exactly that most significant effect in the results. Okay, more questions there's a comment from not only George about what about bootstrapping techniques to get estimates of uncertainty around, oh, that's just jumped, what happened? Okay, what about using bootstrapping techniques to get estimates of uncertainty around some obtained results for a given sample? Can it be useful to estimate an analog of power for existing studies?
If I understand the question right, the answer is yes. I mean, bootstrapping is this amazingly generalizable tool that can give you a lot of information without having to repeat the study multiple times. And so if you want to get a measure of the uncertainty of anything that you're obtaining where you're aggregating over multiple trials, bootstrapping is a great way to do it. But I'm not sure if I'm fully understanding the question.
I have a question related to this, actually. I've been playing also around a little bit with bootstrapping, and I'm always wondering, how big does my sample need to be in the first place? Because anyway, like bootstrapping is basically picking from your data as that you have collected repeatedly with replacement, and in order to estimate what the world should look like, or like the world of data should look like. But if your world is tiny in the first place, I don't know if that analogy is clear for everybody, but so how many trials are enough? I tried to play, and just a little note, I tried to play, like with just a few points and trying to sample from these points and, looking at the figures in R and seeing that indeed pretty soon there is a shape that appears. But I don't know if you have any further comment on that.
A little bit. I'm not really a math person. I'm more of a logic person, but the logic behind bootstrapping is very interesting and very clear. But to get at your particular question, what the pros say is you have to have at least 8. So just to reiterate, when you're bootstrapping, what you're doing is you're saying, well, theoretically, we have an infinite population of trials and we've sampled some number of trials from them. but you've run one experiment, so you only have one sample of trials. So you simulate new experiments by sampling from the trials you have, but with replacement. So if you've got 100 trials, you simulate a new experiment for a given subject by grabbing 100 of those trials at random with replacement. So you get 2 instances of some trials, 3 of some, 0 of others, etc. Then you can do this over and over again, and you're using the recorded data as a proxy for this hypothetical infinite population. Now, when you do that, and you're going to do it over and over again, like we typically will do like 10,000 times, where we grab a random sample of trials, make the average, measure the value. If you don't have enough trials, you're going to end up with the same random sample on multiple iterations of the process. And what the experts say is that, once you get beyond about 8 trials, it's very unlikely that you're going to have repetitions. So 8 is sort of a real minimum, but the quality of your estimate of the data quality, that is the error of your standard error, goes up as the number of samples goes down. And that's not just true with bootstrapping. It's true even if you had access to the infinite population of trials. And so how many trials do you really need to accurately estimate your data quality? And this is something we're currently starting to explore. What we found informally is if we have at least 20 trials, we seem to get really stable, meaningful values, and then it starts to decline from there. But we really need to do simulations, which is a word that I keep hearing in this session. Simulations are awesome. I love simulations. So we have to do some simulations to really ask, well, what are the conditions, and does it depend on the size of the effect? What does it depend on? So my guess is that the answer to the question of how many trials do you really need to get a good estimate of the data quality is going to be what I like to call a 2-word answer that begins with it and ends in depends. And what we want to do with simulations is figure out what it depends on so that we can give people practical advice.
Indeed, it always depends. When I teach my start classes, I always tell them, you're going to ask me a lot of questions. The answer will most of the time be, it depends. But we can give you the tools to find out the answers. The best way is if you learn enough programming that you can run your own simulations, then any question that pops to mind, go down, code it, you'll have your own answer. And most of the time, nobody else will have that that answer for you, because you'd be studying something very specific in a specific field. The question is, how do you set up those simulations? I'm really hopeful with those people releasing those big data sets with hundreds or thousands of participants, that more and more will be able to do data-driven simulations. So we can answer questions, but with data that are much more realistic than the typical, let's assume everything is normal and blah, blah, blah. Okay, so the chat is very active. There's a lot going on. People getting excited with filters. Steve, I'll let you pick up if there's some stuff you want to talk about here.
Sure. So there's this comment from Julio about being especially worried about high-pass filters. And high-pass filters are definitely very dangerous when you go above about 0.1 hertz. You can introduce artificial peaks into your data. People draw completely incorrect conclusions by over-filtering their data. And so I have a couple of papers written about this sort of thing. There's one that's Tanner et al. That I would particularly recommend that shows how high-pass filters with real data and simulated data can introduce artificial peaks and lead to wrong conclusions. With respect to sort of the issues at hand here, when you're quantifying the precision or the data quality, that tells you how consistent your results are, but it doesn't tell you if your result is accurate, that is the correct value. So that would be the issue of bias as opposed to precision. So you could do lots of things that make your data more precise, right? Just turn off the amplifier. You'll get a value of 0 on every trial. It will be really precise, but it will then be inaccurate. So you do have to always keep in mind, are you biasing your data? Are you destroying your accuracy in your attempts to increase your precision?
All right. I'm losing track of all there's a lot of questions. There's a big question from Nico Bush. If we can put Nico live, because it seems to be, I'm not sure I get the understand the question. Yeah, filtering. I mean, obviously, we could have a whole session on filtering and all the damage it's done to the field.
Anyone has that paper Steve was mentioning?
Hi.
Tanner?
Can you see me?
Hi, Nico.
Can you hear me?
Hey.
Hey, Nico.
Hi. Thanks for inviting me to the stage.
Oops, we've lost you. Or
do you hear me?
Yeah.
Nico, you're not moving anymore. Or am I the only one?
No, Nico is live. Good.
Yeah. Okay, we've seen your hands. Yeah.
Okay, I see thumbs up. Others shake their heads. I keep talking, and you need to give me a feedback. Maybe type in on the command line. Okay, so awesome. Thanks for inviting me to the stage. It's an amazing conference. Thanks to the organizers. It's amazing. Question to Steve about your measure for signal quality, which is, as you explained, dependent or with respect to a specific dependent variable, what you call a score. And I understand why that's useful.
Nico, we lost you.
We can hear it. I think it might be on your end.
I see both thumbs up and thumbs down.
Okay.
No, you're good. You're good.
I keep going. I'm not sure what to do. I understand why that's useful. However, in some circumstances, I can imagine it would be useful to have a quality measure that is independent of a dependent variable. Like Steve, your example in the very beginning with this drifty channel, that was surely independent of a dependent variable. Can we have such a measure of signal quality too? Or can you imagine how to adapt your measure to this kind of circumstance?
Well, I would like to try to persuade you that it's really not a good idea to try to come up with a score-independent measure of data quality. So, for example, those low-frequency drifts won't be very important at all if you are doing like a 10 hertz or 40 hertz steady state evoked potential experiment. Those drifts really won't matter very much. You can easily filter them out, etc. If you did want to have just a general metric that was independent of score, you could just take the root mean square of how the voltage changes over time, right? Just how much overall activity there is, under the assumption that the signals that we're looking at tend to be small and small relative to the other sources of noise. So the bigger the overall activity is, the noisier it is. But that's a pretty coarse assumption. But I think it would be the most generic measure that I could think of.
Okay. Maybe a question for Aaron. And that's a tough one from Quentin Moreau. When you're coupling EEG, MEG measurements with behavioral measures, probably to look at brain behavior correlation, then how do you compute your effect sizes? You know, which aspects should you prioritize when you do a power analysis?
We don't hear
myself. There we go. So let me see if I understand the question correctly. So the idea being like looking at like a continuous predictor to the outcome from the MEG data. Is that what we're getting at here? Or I'm not sure I understand the question.
That's how I understand it. So you not only have, you want to do your power analysis, but you look at the relationship between things that are very different, behavior and brain activity.
Yeah, I mean, I don't want to sound like a broken record, but like there should be ways to simulate this, right? So you can, again, let me just put the package in the chat here. The SimStudy package is going to allow a lot of flexibility in, you know, what you're doing, like whether it be like, you know, count data. So like some behavioral activity, like, you know, so a count data that I actually consult on a lot is actually like stool passes per day. So if we're doing like a study on like diarrhea, essentially related to some medical outcome, so we may have that as an outcome variable or a covariate, or age or something else. So all those different things can be incorporated within, you know, a more broad simulation. The unfortunate thing is, like I said, I'd love to have that all in one function that I can provide to you all that makes that process quicker, but it's really going to take the time, like you said, to learn the programming skills and make those specific to the specific things that you're doing with your studies, and the type of data you're working with. So let me just put this in the chat real quick. It's a really powerful package as far as what you can do. Did that answer it? Because maybe it's a little my not understanding of EEG research.
Okay, I don't see any comments on that. Yes. Well, we're officially running out of the extra time now. Maybe. So we've established that essentially we need to run simulations, a lot of them, and maybe we need to organize something around that. Teach people, you know, how do you set up a simulation, starting with, you know, bare bone examples, and how you build up progressively to something more and more complex. Yeah. Maybe invite Lisa DeBryan, for instance, but then take it to, you know, levels much more complicated, where you take into account sources distributed with all sorts of potential biases. How do you combine across different scales of measurements and integration from trials to participants? Yes, it could be a whole week spent on that.
It could
start
be a
easy
next
and
cutting EEG event.
Yeah,
let's do
I
that.
think that'd be brilliant. Well, in MATLAB, please. Or why don't we do it all in Python? Could be interesting. R could struggle, you know, if it's R is fine for quite simple data sets. If you want to take it to big distributed sources, I don't think it's gonna happen in R. Could be there for a while. Yeah, Python, please. Yes. Well, let's see. It'd be interesting to see what people want and what language. Oh, Julia, yes, indeed. Well, thank you all. It's been an amazing session. There's obviously a big appetite for statistics and for all those questions, and it's nice to see so many people. Thanks to all of you. And I don't know, do we officially have a few more minutes? I mean, thanks everyone. Yes. There's some more sessions coming up. It'd be nice to get people's feedback on the session and see what you'd like to see more of, what topics you'd like to be covered, and so on. For the next LiveMEEG.
We are way beyond the schedule, actually. But
yes, we are.
But they are beginning in 15 minutes the next session. So
yes, time to take a break.
Right. Okay. Thank you.
All right.
So much.
Thank you all.
Yeah. Bye bye. Ciao.
Cheerio.
Bye bye.
Goodbye.
Bye.